Welcome back to linear algebra. I'm actually really excited because I just remembered we finished reading yesterday, so we're going to be into practice problems today. Before we start, though, we're going to jump into Anki, as usual. 3 flashcards, what do we got? What does it mean to state that a matrix has a size m, xn? It's got m rows and n columns. How might you express a solution of a linear system as an ordered n-tuple? Basically, parenthesis, depends on what you describe as the answer, but x1, comma, x2, comma, dot, 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 comma, xn, parenthesis, or sn, yeah. They're a variable, it's good. What is a matrix? A matrix is a rectangular array of numbers. How does it feel? All right, that's it for Anki. So what did we learn about yesterday in linear algebra? Well, we finished this section 1.4, which is on inverses and algebraic properties of matrices. Arithmetic properties of matrices. All right, what do we got? All right, what do we got? I remember we started and finished a section on the properties of transposes. So transpose of a transpose is the original. If you've got a minus b or a plus b within parentheses, the power of transpose, or transpose of the sum or difference, is the same as taking the transpose of one matrix minus the transpose of the other matrix. Same for multiplication. And then there was one more, I think it's if you've got a scalar times a matrix and the transpose of that, it's the same as taking the transpose of the matrix and then multiplying it by the scalar. What else would we have talked about? Powers. I think we finished the powers. We might have been in the section on powers. What would have been the power after powers? I'm not exactly sure. Power, let's just check what it was. Right. We finished powers of a matrix, and then we talked about polynomials of a matrix. That was another section. Matrix polynomials, I think is what it's referred to as. All right. So it's pretty simple. If you have a polynomial function, and it's f of x, you can plug in the matrix for x, and then also multiply the constant by I, which is the identity matrix. When we're talking about matrix polynomials, I think we're just referring to square matrices. Yeah, I think all of this is basically square matrices only. Transpose is square matrix polynomials, that's square matrix. Matrix powers, or powers of a matrix, those are all square matrices. All right. If a matrix is invertible, so is its transpose. All right. Properties of transpose. Oh, it is algebraic properties of matrices, not arithmetic. Okay. All right. Powers of the same square matrix commute. Therefore, polynomials of the same matrix commute. I could spend more time understanding that, but we've got practice problems to do, so that's gonna hopefully help work through and find what I don't understand and help deepen the understanding that I already do have. All right, I forgot a lot of stuff. It's hard when the stuff's so abstract, and this is all new. I've never heard of the term matrix polynomials until like 2 days ago, or yesterday actually, so that's why it's still hard for me to be like, yeah, we talked about this and this and this, because it's all so new, so I'm forgetting it. matrix powers. So when we have a plus b in parentheses, all that squared, typically in algebra, you could say a squared plus b squared, a squared plus 2ab plus b squared, right? That's the foiled out version or the expanded version. But you can't say that necessarily in matrices because they do not commute, right? Matrix multiplication does not commute. So the best you can say is a squared plus ab plus ba plus b squared. But if they do commute, then you can say the 2ab. All right. All right, yeah, that's everything from yesterday. So we're gonna get started here in section 1.4 problems. So I'll be back at the end of the day just to recall quickly what we got through. All right, so we finished a few problems. This first one was just using like some examples, verify the associative law of matrix addition. So I think we did that one all right. Similar thing, but verifying that the transpose of a transpose is the original. That's all right. Then this one was the first problem. The inverse, finding the inverse. I don't know why I couldn't find the inverse. I tried to verify the answer was not right. We found the determinant. I think I did that right. I think I found 1 over 20. And then I thought the inverse is 1 over the determinant times. You flip the order of the A and D, and you flip the order of B and C, but then you multiply both of them by -1. I thought that's how you figure it out. Obviously, that can't be right. So tomorrow, we're going to figure out how to... I sat with that, getting pissed off for quite a long time. And saw that the next 1, 2, 3, 4, 5 problems all had to do with inverses, so I couldn't really do any of those. So I skipped down to 19, which was just finding a cubed, given that a is this, and I think I got that one right. So tomorrow we'll figure out the actual formula for finding the inverse, which is actually a huge part of this chapter. Who would have guessed, or this section, who would have guessed, considering that the chapter or section title is inverses, semicolon, algebraic properties of matrices. So that's it for today. Talk to you tomorrow. See ya.